Hello class, this is a video tutorial on discrete probability distributions. Probability distributions are merely a way to display results and their probabilities of an experiment. We will only be focusing on discrete numerical data and work with continuous numerical data next year. So let's get into an example just to get an understanding of the notation of these discrete probability distributions. First, we need to understand what this notation here is. P of capital X. X is the experiment that we are running. An example of this is P of X is equal to results on a regular dice. Little x represents the individual results that can occur on the experiment. So for example, on the regular dice roll, we could get a 1, 2, 3, 4, 5, or 6. Get the idea? And now, P of X is the probability of this one outcome occurring. Well, rolling a 1 on a dice, the probability of that is 1 in 6. And it's the same for all of them here. This symbol here is called sigma, and it just means the sum or the total. In this case, we're taking the total of this row here. The sum must equal 1 because probabilities must all add up to 100%. Each individual outcome must be between 0 and 1 because it doesn't quite make sense if there's a negative probability or if the probability of a single outcome being greater than 100% or 1. So we can create probability distributions from all our prior understandings, such as two-way tables, probability trees, and even functions. So our experiment in this case is the number of heads from the throw of 3 coins. We've seen before that we can represent this using a probability tree. We could get heads, 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 tails, heads, and so on. I've drawn all the possible results here already. So now, what's the probability of getting 0 heads from the throw of 3 coins? Well, 0 heads is the same as tails, tails, tails. There's only one result like this. That's going to be 1 in 8. The probability of getting 1 heads in the throw of 3 coins. So let's look at all the results here. And let's count the individual results that have only 1 heads in them. There's 1, that's 2, and that's 3. So that's 3 out of 8. The probability of getting 2 heads. Once again, let's count the results that have 2 H's in them. It's 1, 2, 3. Once again, that's 3 out of 8. And for this one, 3 heads, there's only one result there. That's 1 out of 8. Now if you add these results here, it's 1 in 8 plus 3 in 8 plus 3 in 8 plus 1 in 8. That will give you 8 out of 8, which is the same as just 1. Here's another example. The probability of, the experiment that we're running is the sum of 2 rolled dice. We can show this using a two-way table. Here are all the results of dice 1 and all the results of dice 2. And I'm showing you one example here. If dice 1 were 2 and dice 2 were a 3, 2 plus 3 is 5. So that's just one example here. I've tabled all the possible results of the sum of 2 dice, and now we can easily count all the individual probabilities of 2. Well, for 2, there's only one square that has 2, and there'll be 36 squares in total. So that's 2 over 36. The probability of 3, there are 2 squares with 3, and 36 squares in total, so 3 in 36. I'm hoping you're seeing the pattern here. For 4, there are 3 squares here. Sorry, I just missed that. There should be 1 and 2. Getting confused with the number themselves. And for 4, there's 3 squares. So that's 3 in 36. And the rest of them are shown as follows. So we can calculate using these probability distribution. We can easily calculate the probabilities of each result. The probability of 3 is just 2 in 36. The probability of x, so the result being greater than 6, well, that's the sum of all of these numbers here. Well, we can easily add that. 1 plus 2 is 3, 6, 10, 10, that's 20, plus the 6, that's 26 in 36. The probability of not 12, or the results not equaling 12, that means it's just everything else here. Well, that's the same as 1 minus 1 in 36, which is 35 in 36. Here's an example of a function of sorts. So this function says if you get a result of 0 or 2, we use this function. If you get a result of 3 or 4, we use this function. If the result is not 0, 2, 3, or 4, so everything else, we get 0 for the probability. Well, let's fill out our probability distribution table. So if the result is 0, we substitute 0 into this function here. So 4 take away 0 is 4 times 1/16. That's going to be 4 in 16. The probability of 1 is just 0 because it says anything else is just going to be 0. For 2, there it is. We substitute this value into the function. 4 take away 2 is 2 times 1/16 is 2 in 16. 3, substituting 3 into our function there. 3 take away 1 is 2. 2 times 1/8 is 2 in 8. And lastly, for 4, substituting to the function, that's 4 take away 1 is 3. 3 times 1/8 is 3 over 8. These probability distributions can be written as decimals and graphed using histograms or regular number planes and coordinates. So here it is using decimals. I've drawn it here using a histogram. Or you could just plot each individual point as you would a coordinate on a number plane. So 0, 0.25, there's the point, the coordinate there. 4, 0.375, there it is there. Now, since probability distributions must sum to 1, we can determine whether a function is or isn't a probability distribution. Or determine unknown probabilities in this distribution. So let's do 2 examples here. Let's determine whether the function p of x equals x minus 1 over 3, where the results can only be 1, 2, or 3. Let's figure out if this here is or isn't a function. We can do this by making a distribution. So, The results can be 1, 2, or 3. Substituting 1 into our function here. 1 take away 1 is 0. So it's going to be 0 over 3, or just 0. Substituting 2. 2 take away 1 is going to be 1. 1 over 3, well, 1 over 3. Substituting 3 into the function, that's 3 minus 1, which is 2. It's going to be 2 over 3. Now if we take the sum of these, adding them all up, 0 plus 1 over 3 plus 2 over 3, that's going to be a total of 1. So this actually does add up to 1. Therefore, this is a probability distribution. If, for example, we expected one more number, let's say if 4 could have occurred, if we now substitute 4 into this function, 4 take away 1 is 3, 3 over 3 is 1, and now if we were to add all of these up, we get a total of 2. In that case, this wouldn't have been a probability distribution. In this instance, it is. Lastly, a probability distribution is tabled below. So we're being told that this here is indeed a probability distribution. Well, because of that, we should be able to calculate what the value of C is and the probability of 4 occurring. Now how we do this is we always recall or use the feature or the property of probability distributions that they must add up to 1. So adding all these up, let's do the total, is equal to 0.1 plus 0.2 plus C plus 3C, I'm just adding each of these up, plus 0.3 plus 4C. All of this must equal 1. Adding up all the values, 0.1, 0.2, 0.3, that's a total of 0.6 plus C plus 3C is 4C plus another 4C is 8C equals 1. Solving for C, we get 8C is equal to 0.4. C dividing by 8 on both sides will be 0.05. Well, since we have this, C is equal to 0.05, we can just substitute it here. 4 times 0.05 is just 0.2. So the probability of 4 is 0.2. So I hope that gave you an insight into probability distributions. Hope you saw that it's not too difficult, and it's just another way that we can represent data or probability experiments as a table, and you can start interpreting this as you would a function and a table of values. So I hope to see you in the next video. Best of luck.